we are going to be taking a look today at some properties of logarithms. Now, the cool thing here is it goes along with something we've already done. We've already done rules of exponents, and basically the rules are exactly the same, except now we're using logarithms, and I have weird funky stuff going on here. Okay, so basically our product property back when we were doing exponents was if you're multiplying, you add the exponents. Well, same thing here. If you have logs and you're multiplying them together, multiplication becomes addition when we expand, and addition becomes multiplication when we condense. Explanations of that coming here momentarily. So then, once we get that situated, so quotients, normally when we were dividing before, we'd subtract the exponents. And that's going to be the same thing here as well. Now the difference on power property, because before, power to power, we'd multiply the exponents. Not quite what we're going to be doing here. Basically what's going to happen here is if you have an exponent, it's going to swing back down to the front of your problem and become that particular log's coefficient. And we'll kind of explain how that works. But those are the three things we're basically going to be working with. So when we're attempting to use properties of logs to evaluate expressions, and I don't think I'll have to worry with you guys as much about this, but again, when it says use a property, it means we don't just want to plug numbers into the calculator like using change of base. So what we're going to do is we're going to take that 4 out, and we're going to go, ooh, that's not really 4. That is 2 to some power in disguise. So 2 to what power would get me to 4? 2. You're like, okay, what did I just do this for? Because again, from way back when we were doing this last week, this log base 2 and 2 are inverses. So since they're inverses, they take care of each other. And then when we do power to power, you'd multiply the exponents. So we just multiply whatever values happen to be left, which in this case would be the squared on my 2 and the 5 exponent that's already there. So basically what we're doing with this, with our properties of logs, is manipulating them into something where I can use an inverse. So like for instance here, now this might be a little more interesting. I want to have log base 3 and 3 because then they would be inverses. They would take care of each other. But how do I turn 3 into 1/3? Okay, use that -1 exponent to make a reciprocal, to flip it, so then the 3 and the log base 3 are inverses and get me to a solution. And that's the whole idea, again, with property of logs. Well, if I have two numbers, do I have to do them separately? I could, but why do I want to do that much work? So if you can simplify what's inside, you can. And then I can still use my property of logs to get to the solution. All I do now is I turn the 27 into a 3 to some power, like 3. And again, the inverses take care of themselves, and whatever I have left as far as exponents are what my solution's going to be. And that's going to be true with any of these. Now here, oops, four to what power gets me to 64? 3. 4 to the third is 64. And again, my inverses leave me with just my exponent. And again, some of you may wonder, well, could I do like we did before and say 4 to what power is 64 and just get the answer? Sure, but I just want to see what step you're using somewhere in between with those and make that work. So then we actually get to start using some of this. Expand the following. In other words, take it from small and make it really big. So here's how this is going to work. Typically with these, anytime there's division or a fraction, we're going to deal with that first. And division, we just got done up here saying, is going to turn into subtraction. So here's how we're going to do this. We're going to split this into my numerator minus the log, okay, of my denominator. Division becomes subtraction. But then I go back and I say, okay, are there any other properties here that I could use? And there are. The product property, am I multiplying anything? Yes, I'm multiplying 7 times x to the third. And we don't always think about that. We're like, it's one term. But they're being multiplied. So I'm going to break this one up. And we're going to have the log base 2 of 7 plus, since multiply becomes add, log base 2 of x cubed. Multiply becomes add. I've still got my minus log squared y here on the end from my division in the first part. So we always want to do the product and the quotient properties first with these, with some rare exceptions. At the end, if I have an exponent then, a power, and I do here, remember we're going to take that and that comes back to the beginning of that particular term. Not all the way to the start of the problem, but just that term. So my last one, log base 2 of 7 plus 3 log base 2 of x, because the 3 moved from the exponent to the coefficient, minus log squared of y. And that's as far as I can go. When I have no more products, no more quotients, and no more exponents, that's how I know when I've completely expanded it to the largest that I possibly could. You're going to say, Hardy, you just got done saying we always do product and quotient first. We're not doing power. Well, everything has an exception. So here, the fraction is going to become subtraction, just like we talked about here, except I'm going to take my squared because it needs to go with each of my terms here. And I'm going to take them along. You're like, why don't you just make it 49 and 81? Because remember, I want to expand this. And when I'm expanding, exponents don't just get multiplied. Exponents become coefficients. Again, once I no longer see exponents, or any products, or any fractions, or division, that lets me know I've simplified this as much as I can. Bless you. So, every time, lots of multiplication. So 2 times the x squared, and then times the y. So I got the 2, and then the plus breaks up into another term, which is x squared, which breaks up into another term, which is y. There are no fractions or division, but I have one exponent that'll need to come back down as a coefficient of that particular term. No more exponents, no more products, no more quotients, no more expanding. And just like we do with anything, I mean, when we're doing equations, sometimes we'll divide, and then we multiply, we add, and then we subtract. We also want to be able to go both directions with these. So sometimes we may be given logarithms that are in multiple terms, and we want to write them as a single. In other words, we want to smash them back together, or condense them. And basically, it just means everything we just did, we go backwards. So when we were doing these, we did the exponents last. Now we're going to do those things first, but they're not exponents, remember now. They'll be coefficients. So if you have a coefficient, my first job is going to be to turn it back into its exponential form. And some of you will start feeling comfortable and you'll be able to do multiple steps at a time. But for now, just kind of keep it simple. So once I get here, I say, okay, that's my only exponent. I go from left to right, just like I'm doing with, reading a book or something like that, and start combining things. Addition turns back into multiplication, and I'm going to simplify the 2 squared as well here. So 2 squared is 4 times 6, and I'll simplify that some more here in a minute, because I just want to see with the examples how this all works. And then minus subtraction goes back into division. So I'm going to have the log of 6 times 4, which is 24, divided by 3. If you leave it that way, that'd be okay. If you're like, but I know 24 divided by 3 is 8, I'm fine with either. Because either way, you're showing me you understand how to kind of work it backwards into its original single logarithm. And to be perfectly honest, the thing that tends to get people the most is one special case, and it's actually going to come here in number 13. People want to take this 5 and swing it back up here as an exponent, but it's not. Because when we talk about it being a coefficient, it has to be in front of my logarithm, in front like this is. This 5 would have to be here. It's not. This is part of my x squared. So here I just look and say, well, there's an addition. So I'm going to multiply these together. 5x squared, replace the plus with a times 3. And again, I can leave it that way, or I can go ahead and simplify it. Because again, the big thing here is showing the understanding of addition to multiplication and subtraction to division. Once you get that shown, you're good to go. But be careful on those base numbers. And then the last one, same idea. The kicker on 14 is when you're turning these back into exponents, do not take this minus with, because if you do, that would change the value of things. Because if I make that a -2, this would have to become plus, and then it becomes multiply, and we don't want that because minus is going to be divide. So I'd have the log of base 4 x cubed, the minus becomes divide over y squared. It wouldn't look like that at all if I would have put plus in the middle. So that's one thing that we're going to run ourselves into. We're also going to run into some things where we may get a problem here or there where we can't do something in our head. This is where we use this fancy schmancy change of base. Because, for instance, here, I could try to set this up as an exponent, 3 to the x equals 7, but unless you want to play a lot of guess and check, it's going to be hard to figure out 3 to what power is 7, since it's not a perfect square or cube or anything like that. So we have an option. We can take the log of our physically larger number, our of base, and divide it by the log of our base. And this one is strictly one we're going to use the calculator for. The thing about logs, though, is they already start you with a parenthesis, so I don't need an extra one, but I do need to close it on the back end. Because if I don't, I'm going to get the log of 7/3, and I don't want the log of 7/3. I want the log of 7 divided by the log of 3. And typically, we'll round to the nearest thousandths to 3 decimal places on these, unless you're given a specific instruction to do something different. So whenever in doubt, if you can't figure one of these out, just take the log of your of value divided by the log of your base. And that'll be the same on all of these. And that also works if you get natural logs that you're asked to do the same thing with. Ooh, we get to round all the way up. My 6 is going to make me round up from 199 to 200 here. clear out for this last one. So basically, you hope for lots of these because we're letting the calculator do every little bit of the grunt work on these. This is now where the fun is going to start for some of you that just got the secondary sheet from me, because things are going to change. So let's see here. How are we going to tackle this? Well, let's try something. Okay. Some of you may want to find something scratch-wise to the side if you no longer have a back, as we're going to make some slight adjustments to some things, and I will get you copies of the legit ones here ASAP so we can try to get this set. I might even be able to sneak out of here fast enough to go make a copy over in the workroom, but we'll see. So when you get over to the back, it's going to ask you to use the inverse property of exponents to simplify each expression. This is some old school notes. If parents ever see these, you're going to be like, this is how I used to have to take notes anyway. These are the ones that are simpler because I'm not going to make you take things out of disguise. Everything is already going to have its inverse there for me already. Log, base 6, and 6 are inverses. They cancel and just leave me with that exponent part that's left. So basically it's like we were doing in the first section, except now we have the setup already for us. Even if it's an exponent. Talk a little about exponentiating. 5 and log base 5. Same, just leave me with whatever's up in the exponent. So it doesn't matter if the logarithm's in front or if the logarithm is in an exponent form. I'm still going to have the same ability to be able to wipe those out since they're inverses and take whatever value happens to be left. So you're like, okay, that's not terrible by any means, but you know, what good might that do me to be able to do something like this? Well, glad you may have thought of this. I have a second number 20. This is interesting. I'll write this down and then I'll talk about it here for a minute while those of you are kind of jotting down a couple of things, because it'll allow me to discuss a little bit what we're after here. Okay, what we're after here is figuring out what x equals. So we're going to have to use some properties of logs, including doing a little bit of condensing to be able to solve these. So here's where the fun starts. Any condensing I can do, like over here, I see the plus will be multiplied, but I also see this coefficient out front. So I'm going to move that back up here. And I also notice that the plus will make me multiply these. Just like I said before, I'm going to write out a little bit more with these than I normally would, just so you can see everything I'm doing step by step. So when you go to do it, you can be like, oh yeah, that's what we were up to here. So once I get my exponent taken care of, because I always do that when I'm condensing first, the add's going to become multiply. And we're finally going to be to a point that we can start dealing with this. You're like, but wait a minute, they got that log a there. Right. So here's basically what we're doing. We have this thing that's called the one-to-one property of logarithmic functions. And it tells us that if you have two things that have the same base, both have a base of a, whatever you're taking their of value to, they're equal to each other. So in other words, once we get to this part, we can ignore the logs at this point and just take what's left in the parentheses, set them equal, and solve it. Now, sometimes that'll be simple, sometimes there'll be a little more work. Like here, I have a quadratic term with x squared, so I need to get all my terms to that side and then factor it. because this will allow me the opportunity to be able to solve for x. So, a little bit of factoring coming back in. It never really goes away once you learn it the first time here. Let's see, minus 3 plus 1, negative 6 and 1, yes. So I'm going to go ahead and I'm going to set these each equal to 0 and find that my two solutions would be negative 1/2 and 3. But there's one thing that we haven't talked about yet that would probably be a good time to do right now with an example or two. When you're taking a logarithm of a number, okay, you're like, well, here it's log A. How would I even type this in? Well, that's true. But here, let me just explain something in general. If you attempt to take the logarithm of something that comes out negative, we're going to get non-real answers. We're going to get things that can't be graphed on a regular coordinate plane. So typically, those are not solutions we use. So when it says on here, check your answers, I'm not saying you have to check every single one, but at least check long enough to see if you took these values and plugged them back into the original expression, would you be taking the log of a negative number? If you would, that's not going to be a solution. If I tried to take the log of negative 1/2, that's not going to work. You're going to get a non-real error message unless your calculator is set up to deal with I. But even in that case, it's not going to be, we're going to call it an extraneous solution here and just get our value, okay? As long as it ends up as a positive log, typically they're going to work. But I'll show you a couple where they get decimally that we'll kind of try out too, just to be sure. So be on the lookout for those. Negative logs are not going to be friendly to us. Let me find one that's a little more friendly in regards to that. Okay. Now here, same, but yet a little bit slightly different situation. You're like, okay, well, I could condense something here, and you're like, that's true. So minus, you're like, ooh, minus is going to become divide. So we've got log base 5 of x plus 3 over 2x minus 1 equals 2. Well, now what do I do? Because this has got a log and this doesn't. Well, to get rid of this log base 5, I'm going to do something similar to what we were doing up in that last section. Okay. I'm going to do what's called exponentiate. I'm going to use this base number to get rid of this. In other words, when I come down here, both sides, I'm going to use the 5, and this is all going to become exponents. Okay, that's something we don't talk about much. We talk about add, subtract, multiply, and divide, take a square root. But exponentiating is another inverse or opposite that we can use. And then 5 squared is 25. And now I'm going to work this out from this methodology. So, let me swing this back over here. So I look and I'm like, well, how the heck? Again, I want to get these x's out of here because I can't just start canceling because, again, I've got the plus and minus working. So I'm going to go ahead, multiply both sides by 2x minus 1 because that'll at least get me out of fractional issues here. And I'll distribute on the right. And now at least I can kind of work my way through this. So I can minus my 1x over, add my 25. And this one could look a little bit scary when you first do it because you're like, is that really going to work? And I'm going to have you trust me on this particular one. We're going to do the calculator on the next one. I did a calculator on this when I was putting this together, and it actually does come out correct. So it's not one that we're going to have to worry about, because even plugging this in as a positive number, it's not going to end up being something that causes a negative. And that's why I can feel more comfortable with that. So with any of these, your biggest challenge is going to be just kind of working through some of the stuff that gets a little ugly here. We'll get a couple more of these in. So I get here and I say, okay, let's see. Coefficient becomes exponent. And 5 to the third is 125. Coefficient becomes exponent. 10 squared is 100. And I'm just going to try to keep condensing things. Subtract is division. So log base 2 of x over 125 equals the log base 2 of 100. But this one gets a little easier because I have the same base. And we said before, when you have the same base, basically you're just setting their of values equal. And that is one extremely large number. At least when we're solving equations here. So this is one, if I wanted to check it, because I'm like, well, it's definitely positive. How would I check it? I normally would go to this value because it's going to be a little easier to type in. And I'm going to use my change of base to see how nicely this comes out. So again, remember, when we're doing change of base, if I plug this in, I'd have the log of 12,000, whoops, not 511, 12,500 divided by the log of its base, and I'm going to do each of these separately. So then I would have the log of 125, oops, no, not again. So I'd be subtracting those two values. And I'm not going to yet because you're going to be able to see here in a minute. Now what happened to me? They're like, uh-oh, this is what happens when you go live and something goofy happens. What has happened that this could have gone strangely? Let's see. I may have plugged something in. Oh, I subtracted there. That's going to do me no good. Side note here. They're like, dang. Even the math guy can do weird stuff. It's true. Oh, double log. Because I was going to say, I know this works out right. Why was it not working? But that's because I didn't pay attention to my own change of base rule. That's better. And am I going to end up with approximately that answer? Let's find out. Because I'm rounding, it won't be exact. That's better. Okay. So I actually can tell and see if it actually works that way, and to see that the value is going to be good. But anytime you get that negative, that's where you're going to want to go and say, yep, that one's not going to work. It has to be this value. So here's our game plan, and I'll get this on there again for those of you that I have a feeling those extra sheets are going to show up in a pile somewhere, and I'm going to be like, what the heck is this? So I'll get these jotted down. I'll post them on the website too, and I apologize because I always have extras left of everything, and for me to be that short is kind of weird. So that's what we're going to be taking a peek at tonight and be discussing tomorrow. We're going to kind of build a little bit off of this more tomorrow. So do kind of play with these a little bit. The actual key will be online, and those of you again that didn't get all of these, I will have paper copies because I don't know what the heck happened. It's kind of strange.